Hi, my name is Amir and today I'm gonna talk about our paper MaskLID Code Switch Language Identification through Iterative Masking. Language identification, or in short, LID, is a task of identifying language of a given sentence or document. Since LID is a classification task, after inputting a sentence to an LID, we get the probability distribution over all labels. Here, Turkish label gets the most probability value given this sentence. This sentence consists of one language. Most of LIDs are also designed to perform monolingual language identification over such sentences. Here we have a code switch or code mixing sentence, which consists of more than one language. The two languages involved in this sentence are Turkish and English. When we pass this code switch sentence to a monolingual language identification, we get the Turkish label as the first label, but there is no sign of English as the top 5 languages after computing the softmax. In terms of language ranking, the English label gets the 15th place, which is not a high rank. When we look at the top 5 predictions, we see that most of them are from Turkic language family, and the reason for that is because these languages have more engram available in this code switch sentence than English. To propose a solution for code switch language identification, we introduce MaskLID, which is designed to complement the existing high-performance sentence-level language identifications, and it doesn't need any training. MaskLID employs a strategy to mask text features associated with first language, allowing the LID to classify the text as second language in the next round. For example, for this code switch sentence, after masking the features associated with language Turkish, we ended up to the second sentence, which get classified as English label with high confidence. As for our experiments and explaining how the MaskLID works, we decided to use LIDs based on the fast text architecture. There is two reasons for this. First, LIDs based on the fast text architecture are quite popular, such as GlottLID and OpenLID. Second, fast text architecture is linear, so we can exactly know how much each feature is contributed to the final decision, and with that identify the features associated with each language. Here we show two equations from our paper. The first one is just a normal softmax. If trained fast text LID extracts T features from the input sentence S and get the embeddings X for each of these T features and do an average over them, and then multiply it with the embedding B that the fast text LID learned for each language C. However, since we are interested in each feature xt, not just the average of them, we define a matrix V, which stores the multiplication of each feature xt with the embedding vector of each language C. Here we explain the simplified version of MaskLID algorithm. We first identify the first language, which is, in this case, is Turkish. Then we go and mask features which we, for the first language, in here Turkish, has one of the top beta values among all other languages. We set the beta value before the start of the algorithm with the help of validation data. Now that the features from the first language are masked, the second language can be predicted, which in this case is English. As for the experiment models, we have two fast text-based language identification models, GlottLID and OpenLID. We have two different setups. One is the baseline and the second one is the MaskLID. As for the baseline prediction labels are the languages with the confidence probability greater than 0.3. Here we show two different examples. As a result of our experiment in baseline versus MaskLID, MaskLID increases CS language identification by a factor of 2022 in Turkish English, 2022 in Nepali English, by 6 in Hindi English, and by 5 in Basque Spanish. As the takeaway, in this work we present MaskLID, a simple yet effective method for a scalable code switch language identification. MaskLID doesn't need any training, and in our experiments, MaskLID increases CS language identification by a factor of 5 to 22. You can also find our code open source.